Okay, hi everyone. This is CHEN 422 Chemical Reaction Engineering, week number 4. Today we'll be talking about combinations of reactors and reactor size comparison, which is chapter 6 from the Levenspiel book. And this presentation will only focus on single reactions, so just keep this in mind. So all these equations are only valid for single reactions. So just a few announcements. So week 4, September 15th, we'll only talk about reactor size comparison. I've decided not to discuss reactor economics for now, and we'll finish reactor size comparison this week. Homework number 3 is due today by midnight, and homework number 4 will be assigned, and it's due a week from today. A few points for you. Next week will be a review week, so I'm just going to go over what we covered so far. And then the week after, which is September 29th, will be exam 1. The exam will be held during your scheduled lecture time from 2 p.m. to 4:30 p.m. So please be aware of that. Exam will be done remotely, so we'll do it using Zoom. And I'll give you some instructions closer to the exam date. Your exam will cover weeks 1 to 4. So basically we'll cover kinetics of homogeneous reactions, IBR kinetics, introduction to reactor design and ideal reactors, and reactor size comparison. Expect your exam to be a mixture of both multiple choice and problem solving. You should expect maybe 10 to 15 multiple choice questions, just testing your general understanding, maybe some quick math, and then 3 or 4 problems which you need to solve by hand. And as always, the exam all of it will actually be from your homework and your slides. So if you study these, you'll have no problem getting an 85, a 90 easily. Okay, so let's start talking about reactor size comparison and what do we really want to achieve in this lecture. So when we're doing size comparisons of single reactors, and specifically we're interested in comparing the size of a PFR and a CSTR, okay? So before doing this, let me just go to the whiteboard and let's just have a quick review of the different types of reactors. So if you recall, there are 3 types of ideal reactors, right? First one is your ideal batch reactor, right? IBR. Sorry. IBR, which is ideal batch. And the performance equation for an IBR is T is equal to CA naught, integral from 0 to X. Okay. 0 to XAF of dXA over minus RA. And we can write this in terms of concentration as integral of minus CA naught to CA of dCA over minus RA, right? And just a few things, RA, this is your reaction rate. CA naught is your initial concentration. And XA is the conversion, right? So just the second type of reactor we discussed is the CSTR, which is the continuous stirred tank reactor, also referred to as a mixed reactor. And the equation for the CSTR is V over FA0. Performance equation is equal to tau over CA0 is equal to XA over minus RA. And again, just a few pointers. This is your molar flow rate. This is your space-time. And again, this is your initial concentration. This is your reactor volume. Okay, and for a first order reversible reaction, you can write this equation as, for, let me change the color here. And for a first order, basically A going to R or going to S, whatever it is, you can write it as tau K is equal to XA over 1 minus XA is equal to CA0 minus CA over CA, right? And this is a CSTR performance equation for a first order reversible reaction. All right, so the third type of reactor we talked about after the ideal batch reactor and the CSTR was the plug flow reactor. So third type of reactor, let's put it here, was a PFR, and this is your plug flow reactor, right? And the performance equation for a plug flow reactor, we said V over FA0 is equal to tau over CA0 is equal to integral from 0 to XAF dXA over minus RA. And we said it's very similar to the equation for an ideal batch reactor because, PFR, there is no mixing, unlike these two reactors where I have a lot of mixing, and a PFR basically behaves as a bunch of small batch reactors just pushing each other along, okay? Alternatively, you can write the performance equation for a PFR as tau is equal to CA0 from 0 to XAF of dXA over minus RA, okay? So these are the performance equations of the three reactors. Let me just draw some diagrams just for you to remember what we're talking about. So we said a batch reactor, basically I just have a vessel and I load it with some chemicals at time 0, and then I take out the chemicals at time equals t, right? And I let the reaction happen in this reactor. And a CSTR, I have continuous flow of reactants and products into a vessel which is continuously mixed, right? So this is CA0 and this is CA, and the amount of time it takes one reactor volume to be processed through the reactor is referred to as tau, which is the space-time. And finally, a PFR, usually represented using a cylinder, and CA0, CA. And the idea of a PFR is this: there's no mixing along the flow direction, right? Whereas these two, 1 and 2, are perfectly mixed, right? So CSTR, so this guy and this guy are both perfectly. So these are the things we talked about in terms of the three reactors, the performance equations you're responsible for, and whatever the reaction rate is, you just plug it in here, and then it just becomes an algebraic problem. You need to, reformat the equation, do some math, some rearranging, and we practice this during the homework. So try to get comfortable with these types of reactions. Other things you need to know. So other side equations which are always good to know. I'm gonna just put them here. A small box, I guess. Just converting between, so we said tau V over V naught is equal to V CA naught over FA naught, and this is your volumetric flow rate. So in case you're given the information you have in the problem consists of a bunch of different, if you're given a flow rate, molar flow rate and a concentration, you can always calculate tau, or you can, if you're given a volumetric flow rate and you want to convert it to a molar flow rate, just keep an eye on all these conversions because they're useful tools when solving problems, right? When, if you're given a piece of information in a certain way. And the second equation we said, which is we use extensively, is XA CA over CA naught, or can be written as CA is equal to CA naught into 1 minus X, right? And XA is the conversion, which is the fraction of chemical which reacted over the initial, or the amount, number of moles reacted divided by the initial number of moles will give me the conversion. So these are the three performance equations which we were talking about. And in this lecture, basically, we want to compare the reactor sizes of a PFR to a CSTR, right? So we're looking for a ratio of, we're looking for the ratio of CSTR, volume of a CSTR, divided by the volume of a PFR. Okay, so let's try to derive this. How about that? Let me just make sure I'm sharing the correct screen. Okay, so let's try to derive this. So I'm looking for, I need to find the volume of a CSTR divided by a volume of a PFR. So how do you approach this? Okay, let's recall some equations. Let's just rewrite the equations we just had. So for a CSTR, the performance equation, we said V over FA naught is equal to tau over CA naught is equal to XA over minus RA, right? So this is the performance equation for a CSTR. Sounds good. So what I'm gonna do is I'm gonna just use this side from here. So I'm just gonna say tau is equal to CA naught XA over minus RA, right? And I'm gonna say that if the spacetimes are equal, then the volumes are equal, right? And this assumption is valid, or this statement is actually valid, it's not an assumption. So if tau CSTR is equal to tau PFR, then basically V CSTR is equal to V PFR, assuming constant density, right? And this statement is valid. Basically, if the amount of time it takes one volume of a reactor to pass to a CSTR is equal to the same amount of time it takes one volume of a reactor to pass through a PFR, then the volumes are equal. Okay, so this will be the equation I use for this derivation. So just for a CSTR, and for a PFR, we'll do something similar. So PFR, let's write the performance equation for a PFR. Again, we said it's V over FA0 is equal to tau over CA0 is equal to integral from 0 XAF dXA over minus RA. And basically, I'm going to rewrite this as, so let me just say this CSTR. And tau PFR in this case will be equal to CA naught integral 0 XAF dXA over minus R. Okay, so I have both equations for a CSTR, and the PFR. Okay, so now let's try to calculate the ratio of these two guys. So let's try to get tau CSTR over tau PFR for a first order irreversible reaction. So in this case, I'm looking at a first order irreversible reaction. A goes to R, or actually let's not look at a first order irreversible reaction. Let's look at a generic reaction, okay? So for generic kinetics of any order, right? Let's have I have just a bunch of generic kinetics K, Ca to the N, right? Just a reaction, any type of order, but I only have one species, right? So but anyways, so for generic or arbitrary kinetics, whichever you want to use, I'm gonna find this ratio right here. So I'm gonna say tau CSTR over tau PFR will be, so let's do it, let's rewrite it this way. So for generic kinetics, tau CSTR will be equal to CA0 XA over K CA to the power N. I'm gonna replace CA is equal to CA naught into 1 minus XA final, right? I'm gonna use final to refer to the final conversion, basically the conversion coming out of the reactor. So now basically tau CSTR will be equal to CA naught XA over K, and then CA to the power N is equal to this equation to the power N, so it's equal to CA naught to the power N into 1 minus XA final to the power N. So this is tau CSTR. Now let's do the same thing for tau PFR. So in this case, I have CA0 integral from 0 to XAF dXA over KCAN, right? I just replaced minus RA with this parameter. And then I'm going to do the same thing. I'm just going to replace CA with CA0. So this will be equal to CA0 integral from 0 to XAF dXA over K CA0N 1 minus XAF to the N. Okay, so I have the tau PFR and I have tau CSTR in this case. So now let's divide them. Okay, I'm going to save the screen, then I'm going to erase this side right here, and let's move to this side and find this ratio which we're looking for. Okay, sorry. Okay, so now we have the 2 taus. Let's move up to this side, and now let's try to calculate the ratio here. So in this case, I'm going to have tau CSTR over tau PFR, and this will be equal to, I'm just going to write the final expressions here, CA0 XA over K CA0 to the N 1 minus XAF to the N divided by CA0 integral 0 to XAF dXA over K CA0 to the N 1 minus XAF to the N, right? You can see a few things will cancel out immediately. So, you know, this, they're all gone. So I just have XA over 1 minus XA to the F over integral dXA 1 minus XAF to the N. And what's the integral of, what's this integral? Or what's this integral? So if I just go here to the side and I say integral of dXA over 1 minus XA to the N, this will be equal to N minus 1 over 1 minus XA to the N minus 1, right? And if I plug it here, so I'm going to get tau CSTR over tau PFR is equal to XA over 1 minus XA to the N divided by N minus 1 over 1 minus XA to the N, right? And this becomes your equation for screen is gone. Here we go. Yeah, and we forgot one thing here. So if I'm integrating this from 0 to XAF, I need to plug in the limits, right? And here I need to plug in the limits from 0 to XAF. So if I plug in the limits, let's just finish our work here. So I get XA over, it's becoming too slanted. Try to straighten this out here. So I get XA over 1 minus XA to the n divided by n minus 1 into 1 over 1 minus XA minus 1, right? Does that make sense? One minus XA no. We wrote the equation completely wrong. Let's just rewrite this. Just retrace our steps and do it properly. I'm making a mess out of this now. Okay, let's go back here and let me just replace. Let me just plug in here. So I get n minus 1 so I'm gonna get actually there's another error here. What's going on? This actually has to be 1 over n minus 1, right? 1 over n minus 1 into 1 minus XA to the n minus 1. And if I plug in these numbers here, I'm just going to get basically 1 over n minus 1 I'm having some technical difficulties here. 1 over n minus 1 into basically 1 over 1 minus yeah, it's not working today. Is equal to 1 over n minus 1 into 1 over 1 minus XA to the n minus 1 minus 1. Okay, and basically if you divide these two expressions, you're going to get the ratio, which is XA over 1 minus XA to the n divided by this expression right here. Okay, so this is the ratio of the two CSTRs. You can derive it yourself. You're gonna get the same answer. And let's move back to our slides because this thing is not working today, so it's fine. So if I do a size comparison of single reactions, and I basically get the expressions to tau k Ca naught n minus 1. So what's written here is that I didn't cancel these constants from this side, which you can do because mathematically, if you have numbers, you might not want to cancel them, you know, because in case one of them is 0. And if you get, and the ratio of these two volumes is basically equal to this expression which we just derived, right? XAF over 1 minus XAF to the n for a CSTR divided by the product of the integral 1 minus XAF 1 minus n minus 1 for n minus 1. So now let's look at the first case for n not equal to 1. And how do we compare the performance, or how do we, what's the comparison of the volume of these two reactors? So in Levenspiel figure 6.1, there's a figure basically. As you can see on the x-axis, I see it's 1 minus XA, which shows you the conversion. And on the y-axis is this equation, which is the ratio of the volume of the mixed reactor, which is the CSTR, to the plug flow reactor. And there's a bunch of lines here, and these lines are arranged according to n, which is your order of reaction. And for n equals 1, I have a bunch of lines, and the straight line, or the solid line, refers to the case where epsilon equals 0. And if you recall, epsilon is the fractional change in volume in case we have gases. And the dashed lines when epsilon is 1, 2, minus half, minus 2, 3, also refer for n equals 1, but I have epsilon other than 0. Similarly, for n equals 2, second order reaction, for a third order reaction, we also have the line, and then for less than 1 order reaction, 0.25 order, 0.5 order, we also have these lines. And this chart allows you to easily sort of get an initial estimate of what you expect this ratio of the two reactors would be. Again, this chart is not perfectly accurate because it's an old chart. It was done sort of by hand on a log-log graph. So if you really want to use the chart, you can reproduce it to get perfect results. If you're using the chart from Levenspiel, just be careful. Sometimes the numbers are off by 0.5 or something. Okay, so for n not equals to 1, we can use this chart, or you should use this chart to get the ratio of the volumes, give you an initial estimate. And just remember that this is for a single mixed flow and plug flow reactors. Just have one reactor. And let's look at one case. So let's say I want to find the ratio of these volumes for a conversion of 0.5 for a second order reaction. So all I have to do is look in this chart. So if XA is 0.5, 1 minus XA will also be 0.5. So I find the 0.5 point, 0.2, 0.3, 0.4, 0.5, and I look for the n equals 2 line, which is this line right here. And from here I can see that, if I read here, it's 2, so the ratio of the volumes is equal to 2. So it's a useful tool to give you an idea on the volume of these two reactors. Okay, and we're gonna start to make some observations. So the first observation is that, it seems that the CSTR will always have a larger volume than a PFR, right? Because this graph starts at 1. It doesn't go below less than 1, right? So a CSTR will always be larger than PFR to achieve the same conversion for the same order of reaction. Let's look, so this is the point referring to this case. Let's look at a couple of other cases. Let's look at the case when I want a conversion of 90% for a second order reaction as well. So if the conversion is 90%, so XAF is 0.9, so 1 minus XAF is 0.1. And I'm looking for a second order reaction here. Actually here, right? I'm reading this line. So in this case, 0.1 and 2, actually this point right here. So the ratio of the volumes is 10. So if I want to achieve 90% conversion for a second order reaction, a CSTR has to be 10 times the volume of a PFR to get the same result. Okay, so CSTR equipment will be much more expensive, much bigger system is needed. What if I want to achieve an extremely high purity conversion? If I want to get 0.99, for example. This is the point referring to this case. If I want to get 0.99, so I want to get an even higher purity of product, even higher conversion, 0.99, so 1 minus 0.99 is 0.01. Second order reaction, it's 100. So I need a CSTR which is 100 times in volume of that of a PFR to achieve the same conversion. Yeah, now we're seeing a second observation, right? As my conversion requirement increases, the volume of CSTR to PFR increases exponentially, right? So at higher conversions, this ratio increases exponentially, whereas at lower conversions, so if I want a conversion of 0.2, for example, you can see that the ratio of the two reactors is not that large. So, as the conversion requirement increases, the ratio of the two reactors becomes much bigger. So you will need a much larger CSTR to get the same conversion in a PFR. Okay. Now let's have a look for n equals 1. So for the case where n equals 1, I'm just going to plug 1 here in n and get my equation, simplified equation as always. And we're basically looking at this line right here, n equals 1. And let's look at a bunch of cases. So if I want a conversion of 0.9, 90% conversion, for a first order reaction, again, I'm going to read it off this chart. X is 0.9, so 1 minus x 0.1, n equals 1, so it's about, 1, 2, 1, 2, 2, 3, 4, right? So it's a bit less than 4, it's 0.91, okay. Similarly, if I want a much higher purity, so if I want a 0.99, much higher conversion, sorry, if I read it off the chart, so 0.99, 1 minus 0.99 is 0.01, and the XAF in this case, or the ratio of the volumes in this case is about 20, right? So again, similar to the previous slide when we're talking about second order, for a first order, I see the same phenomena where, as my conversion requirement increases, the volume of the CSTR increases significantly. So in order to achieve a 90% conversion, I will need a CSTR which is almost 4 times as big as the PFR to achieve the same result. Whereas if I want a 0.99% conversion, I'll need a CSTR which is 21.5 times as large as a PFR to achieve the same conversion. Okay. So this is a very useful chart to read or to get an idea of this type of behavior in terms of conversion to ratio of volumes. The second type of chart you see in Levenspiel, it's chart 6.5. And here I'm looking at 1 minus XA divided by the volume of n number of reactors, so n number of mixed reactors, over the volume of one plug flow reactor. So basically, again, this is for a first order reaction, and I'm comparing the performance of a series of n mixed flow reactors with a single plug flow reactor, right? Previous chart, I was comparing one CSTR to one PFR. Here I'm comparing n CSTRs to n PFR. And as you can see, the lines, these solid lines are in terms of n. So if I'm comparing one CSTR to one PFR, n equals 1. And this line is exactly the same as the line on the previous chart. If I'm comparing two CSTRs to one PFR, two CSTRs in series to one PFR, I look at this line. Similarly, I'm comparing 3 CSTRs in series to one PFR. I look at this line, etc., all the way to infinity, where it's just a PFR. And I have these dashed lines going across, and these are in terms of K tau, which basically refers to your reactor volume, right? Or this metric. If CA naught is the same in both reactors, then K tau is a direct correlation to the reactor volume. And let's have a look at and again, epsilon equals 0. Talking about liquid phase reaction, we don't have any change in volume, or even if it's a gas phase reaction, they're very similar species going in and going out. And again, these solid lines are the number of CSTRs, and let's look at the case where n equals 1 CSTR. And here I'm going to compare two types of scenarios. I'm going to compare the scenario where I'm trying to increase my conversion while keeping the same single CSTR, comparing a single CSTR to a single PFR. Then I'm going to do a second type of conversion where I'm looking at a second type of comparison where I'm looking at how to achieve a higher conversion by numbering up, by increasing the number of CSTRs in series. So again, if I have one CSTR, this is the equation for a CSTR, tau CA naught XAF over minus RA. This is the performance equation. For a first order reaction, RA is KCA. KCA is equal to KCA naught 1 minus XAF, which is this equation right here. And basically tau K is XAF over 1 minus XAF if you want to get the equation for this line. And this is the line here for n equals 1. And let's look at 3 points. I'm going to look at one point where XAF is 0.9. So if I want to achieve a conversion of 0.9, that means 1 minus XAF is 0.1. So it lies here. In this case, tau K is 9, right? So the volume required is 9. And if I want to achieve a conversion of 0.98, a slightly higher conversion, my volume increases to 49. If I want to achieve a much higher conversion, my volume increases to 99. And this is the same conclusion we saw on the previous slide, where if I want to compare performance of a single CSTR to a single PFR, as my conversion requirement increases, my volume requirement will increase significantly, right? So just jumping from 0.9 to 0.99, I need 10 times the volume. Okay, so what about instead of just using one CSTR and trying to achieve a higher conversion by making it bigger? How about I just put a bunch of CSTRs in series? And again, this is the same line as in figure 6.1. You can compare them if you want. If you want to exercise a bit. Let's do a second type of comparison. So in this case, I'm fixing my volume. So I'm fixing the k tau parameter here. And I'm seeing the conversion as the number of CSTRs in series increases, right? So for the case of one CSTR, which is this point, we set tau k is equal to 9, and our conversion is 0.9. And this is similar to what was shown in the previous slide. Okay, what if I want to achieve XAF to be 0.98? So I want XAF to be 0.98, and I want to keep the same volume, right? So 0.98 is, let's say it's somewhere here. So I can achieve this with maybe 2.5 reactors. So if I have, or let's look at it the other way. If I'm looking at 2 CS, so in the case of one CSTR, I can get a conversion of 90% for a volume of 9. In the case of 2 CSTRs, if I just put 2 CSTRs in series, the overall volume of both CSTRs will still be 9. So I'm not requiring a larger volume of reactor. I just need 2 smaller reactors with an overall volume of 9. And in this case, I can achieve a conversion of 0.97. Okay, what if I keep reading this line here? So what about 4 CSTRs? So what if I, instead of using 2 CSTRs, which are small, I'm going to use 4 CSTRs with an overall volume of 9, right? So it's equivalent to dividing my big CSTR into 4 smaller ones of equal volume. And I read the line n equals 4, and you look at the conversion here, you find that it's equal to 0.99, right? So the idea here is, if you want to achieve the same result in a CSTR as in a PFR, you have 2 options. You can either increase your reactor volume significantly, so you keep one CSTR and you just make it much bigger, or I divide this big CSTR into a bunch of smaller CSTRs, and I will achieve a much higher conversion without requiring a much higher increase in volume. Okay, so these are the ideas we're talking about here. Let's just recap quickly. So we're looking at this chart. It's showing the solid lines show the number of CSTRs, and the dashed lines show the reactor volume. And if I'm comparing, and the y-axis the ratio of the volume of a CSTR to a volume of a PFR, and the x-axis is 1 minus XA, which is 1 minus conversion. And if I'm just comparing one CSTR to one PFR, in order to increase the conversion from 0.9 to 0.99, so requiring a higher conversion, requiring almost perfect conversion, my volume of reactor increases significantly. So in order to reach a conversion of 0.9, to increase your conversion from 0.9 to 0.99, I need to increase the volume of the CSTR by 10, okay? Or, the ratio, the volume of the CSTR required to reach 0.99 compared to the volume of a PFR required to reach 0.99 will be 10 times, right? So the ratio of these 2 reactors increases by 10 times. So if I just have one reactor, or I can only buy one reactor, and I look at it this way, then a PFR is always better than a CSTR, right? However, you can achieve this in a CSTR by looking at it in a different way. So instead of making my reactor much bigger, I'm going to break down my reactor into smaller CSTRs while keeping the overall CSTR volume the same. So basically, instead of using one CSTR, which is 10 meter cubed, I'm going to use 4 CSTRs, each of which is 2.5 meter cubed. So my overall reactor volume, my overall CSTR volume is the same. I'm just using 4 smaller reactors in series compared to 1 larger reactor as required, right? And if I do this, if you look at it here, I can achieve this higher conversion. So if I use 1 CSTR, my volume is 9 on 1 reactor, 0.9. If I use 4 CSTRs in series, I can achieve 0.99 conversion, whereas my reactor volume will still be very low, okay? So the idea here is that can you achieve a much higher conversion? If you want to achieve a much higher conversion in a CSTR, it's always better to use a bunch of smaller CSTRs in series compared to using a much larger CSTR in terms of volume, right? So instead of increasing my reactor volume from 10 meter cubed to 100 meter cubed, which does not make sense, then just break it down to 4 2.5 meter cubed reactors, put them in series, I'll get the same result. Okay, so this is just something to think about, and this is actually valid, even though the numbers might seem all, from 10 times as much to almost the same volume, but this is valid, and this comes down to mixing, right? And mixing is one of the most important things when dealing with reactors, and you can become a mixing expert, and their demand is extremely high once you understand mixing, because if the mixing in my reactor is perfect, then the reaction is happening at the highest possible rate, and I'm getting the best possible result from my catalyst. Too often, chemical engineers or chemists, they tend to obsess about the catalyst and think, oh, what if I get a better catalyst? Will my reaction conversion increases? Whereas realistically, it all falls down to these small things like mixing, volume of reactor. There's no point of spending $300 million looking for a new catalyst if I can just break down my CSTR into a bunch of smaller CSTRs and achieve the required conversion, okay? Something to think about is that it's not always the catalyst, almost never the catalyst. It's always the reactor, how you configure the reactor, how you arrange your reactors, etc. Okay. And this just shows you the comparison. I'm trying to achieve the same thing. 2 CSTRs with the same volume, comparison to 1 CSTR, just 10 times the volume, and then 4 CSTRs with the same volume, as opposed to 1 CSTR, which is 20 times the volume, okay? So these are the conclusions for nth order reactions where n is greater than 1, and any duty, the volume of the CSTR will always be larger than the volume of a PFR, right? The ratio of the volume of the CSTR to that of the PFR increases as the reaction order increases. So if you recall, we did it for n equals 2, n equals 1. You can see that n equals 2 required had a much higher ratio of volumes. When the conversion is small, the performance is only affected to a small extent by the type of flow. And again, this comes down to the way your chart is shaped. On the right-hand side, where XAF is low, you can see that this volume is lower, and on the left-hand side, where XAF is high, you can see that this ratio of volumes is much higher. And when conversion is high, then performance is strongly affected by the type of flow, i.e. well-mixed or plug flow. Therefore, if we have to design a reactor with a high conversion, we must describe the mixing very well. This is an extremely important point when you get a job, when you go work in industry, and to understand that, the mixing behavior in the reactor plays a significant role in how it operates. And a lot of the time, reactors underperform because the mixing is not done properly, or it's in a plug flow regime when it should be in a mixed regime, etc. Something to learn, something to always know. One of the important points to learn from this course. And fractional changes in volume on reaction change the volume of ratio of the CSTR to PFR, but to a relatively minor extent. And this refers to this chart up here, where as epsilon or EA, as it changes from minus 2/3 to 2, this change is not huge, right? So this fractional change in volume does not affect these trends significantly. I don't see any crossovers for n equals 1. You don't see any crossovers for n equals 2. N equals 3 doesn't matter at all, etc. So, you know, fractional change in volume would not be a major decision point when looking at the ratio of volumes of a CSTR to a PFR. Okay. So now let's move on to the second order reaction, and let's have a look at the same. We're going to look at the same chart or the same type of theme of charts, but for a second order reaction. Just remember that this chart was for a first order. Let's see if the same thing holds for a second order reaction. So this figure 6.6 from Levenspiel, and says comparison of performance of a series of n equal size mixed flow reactor, the plug flow reactor for elementary second order reactions. So my reaction second order could be either 2A goes to products, or A plus B goes to products, where m equals 1. And negligible expansion, basically epsilon equals 0, constant density. And again, on the y-axis, I have the ratio of n number of CSTRs in series divided by 1 PFR operating by itself. So this is the volume of n CSTRs in series divided by the volume of 1 PFR. And as you can see here, the lines, solid lines are n, which is the number of CSTRs in series, and the dashed lines is k, C naught tau, which is the parameter equivalent to the volume, okay? And again, for n equals 1, for 1 CSTR, we can see here that if you want to achieve a conversion of 90%, so XAF is 0.9, so 1 minus XA is 0.1. The ratio of volumes for n equals 1 is 10. So the way it's presented here, XAF is 0.9, and I want to do this in one reactor, then tau K Ca naught is equal to 90, versus if I want to achieve a volume of 0.99, then tau K Ca naught is equal to 9900, right? So basically, if I want to increase the conversion from 0.9 to 0.99 for 1 CSTR standing by itself, my reactor volume has to increase by what? More than 100 times, right? And this for a second order reaction. A second order reaction, I want to compare the performance of 1 CSTR, the performance of 1 PFR. I would need almost 100-fold volume increase in order to increase the conversion from 0.9 to 0.99. So again, this is a similar problem where the other approach makes a lot more sense, where, you know, instead of trying to get a bigger CSTR, I'm going to get a bunch of smaller CSTRs, put them in series. And in this case, n equals 1, tau K C naught is equal to 90. My conversion is 0.9. If I put 2 CSTRs in parallel while keeping the volume constant, so tau K C naught is still 90. You see this, I drew this new dashed line here. Looking at n equals 2, and I can see here that I can achieve a conversion of 0.95 by just breaking down this large CSTR into 2 smaller CSTRs with the same equivalent volume. Similarly, if I go to n equals 4, same total volume as well, I can increase my conversion to 0.976. So, you know, I can achieve a much higher conversion by just putting a bunch of CSTRs in series as opposed to using a much larger CSTR. Okay. And for second order reaction, so this is just something, you can read the slide at your own pace and try to understand it, but it's not, let's go over it. A plus B, so for a second order reaction, I have A plus B going to products, and M CB naught divided by C naught, and epsilon equals 0. This is the reaction rate. If M equals 1, then this is the kinetics. So I have two cases. When M equals 1, then minus RA is equal to minus RB is equal to K CA CA squared, basically. There's an error here. However, if CB naught is much larger than CA naught, i.e. M is much larger than 1, then my reaction kinetics changes. I get K CB naught CA naught, and I get K CA, and this is called a pseudo first order. If you take a catalysis sort of elective, you're going to learn about pseudo kinetics and things like that. So in terms of the limiting component A, the size ratio of the CSTR to PFR lies in the shaded region as n varies from 1 to infinity. So what this is telling you is for a second order reaction, this value of m is very important. Depending on the value of m, your ratio of CSTR to PFR will fall in this envelope right here. Okay, so just something to understand that for a second order reaction, the ratio of volumes will not be the same, whether m equals 0, whether m equals 1, m equals 2, m equals 3, this ratio of volumes will change. This is really the bottom line of this slide. Okay, let's move on. Now let's have a look at multiple reactor systems. Let's have a closer look at the equal size CSTRs in series, right? Because previously we've established that having a bunch of equally sized CSTRs in series will achieve a much higher conversion than just having a much bigger CSTR. And so you think, why is this possible? How does this make sense, you know? And as I increase the number of CSTRs in series, if I look on this slide, the ratio of volumes actually approaches the volume of a PFR, right? So the ratio of volumes approaches 1. It gets closer to 1, right? So in n CSTRs, the volume for n CSTRs is starting to get closer to the volume of 1 PFR. And this is something we're thinking about, just comparing the reactors. And let's have a look at equal size CSTRs in series. Consider n CSTRs in series. As n becomes large, the n CSTRs start to behave as 1 PFR, okay? Something you need to know. As my n of CSTRs increases significantly, the behavior of these CSTRs in series starts behaving as a single PFR. So just be aware of this. Therefore, if n, in the case of n equals infinity in charts 6.5 and 6.6, is the same as a PFR, right? Hence, the volume of an infinite number of CSTRs in series is the same as the PFR volume for any value of XAF. Okay, and this is of course a theoretical case. A volume of infinite number of CSTRs, you can argue it's infinity, right? But it's a mathematical artifact. What this means as the bottom line here, disregarding the mathematical artifacts and all this stuff, is as my number of CSTRs increases in series, I'm gonna approach the same performance of a PFR of equivalent volume, right? So if I have, say if I have 10 meter cubed, right? If I have one CSTR of 10 meter cubed and one PFR of 10 meter cubed, the PFR will be much better, perform significantly better. If I have two CSTRs, each of them are 5 meter cubed, their performance will be closer to the 10 meter cubed PFR. If I have 10 CSTRs, each of them is 1 meter cubed, their performance will be much closer to the PFR of 10 meter cubed, right? This is just something to understand. And let me just write this here. So basically, if I have, say I have 10 meter cubed PFR versus 1 CSTR of 10 meter cubed, this will perform much better. If I have now 4 of 2.5, the performance is closer. If I have 10 of 1, performance will be much closer. If you go mad and you get 100, each one is 0.1 meter cubed, your performance will be much, much closer to that of the PFR, okay? And of course, there's an economic trade-off, maybe 4 smaller CSTRs economically, capital cost is lower than 1 large PFR. However, 100 small CSTRs are more expensive than a PFR. There's always a trade-off there, but this is just something to know performance-wise. As the number of CSTRs increases, performance gets close to a PFR. And this chart 6.5, as you can see here, as n goes to infinity, this ratio gets close to 1, which is the point we just illustrated. And similarly, figure 6.6, as n goes to infinity, the performance gets closer to 1. Good. Let's move on. So now let's have a look at the equal size CSTRs in series. So let's consider this case here. I have a bunch of CSTRs, 1, 2, I, all the way to n. And the first one, I have a initial concentration C naught, X naught equals 0 because nothing happened, and initial molar flow rate of F naught and the volumetric flow rate of V. Okay, after the first reactors, I get C1, X1, second reactor C2, X2, all the way here Ci, Xi, and then Cn minus 1, X minus 1, and Cn, Xn, V. One thing to note, why is this V the same as this V? This case, we're assuming constant volume, okay? So just be aware of this. This is for a constant volume, sorry, constant density. Constant density, so that's why V is the same. V is your volumetric flow rate, just something to keep an eye on. And let's consider a first order reaction, epsilon A equals 0 and isothermal. So for a first order reaction, the performance equation for a CSTR is this. So this is the performance equation for your CSTR. Is equal to tau is equal to Ca I minus 1 minus Cai over K Cai. Alternatively, we usually write it as, Ca naught minus Ca over Ca naught. And this is the performance equation for CSTR. If I rearrange this, I'm going to get Cai minus 1 over Cai is equal to 1 plus K tau I. Okay, so now what I'm going to do is I'm going to multiply this ratio from Ca0 all the way to Can to get the ratio of Ca0 to Can. So if I do this, so if I get Ca0 over Ca1 multiplied by Ca1 over Ca2 multiplied by Ca2 over Ca3, all the way to Can minus 1 over Caf, I'm going to get 1 plus K tau I to the power n, right? So basically multiply this ratio for each reactor from 0 to n. I'm going to get the final expression, which is equal to, so this is equal to basically Ca0 over Caf or Can, whichever you want, because everything else cancels, and each one of these is equal to 1 plus KTI, right? Each one of these is equal to 1 plus KTI. So there's 1 plus K tau I, 1 plus K tau I, 1 plus K tau I. Multiply all of them, you get 1 plus K tau I to the end. Okay. So I want to, so what's happening here, sorry. I'm basically fishing for an expression, right? So I'm looking for an easier way to represent this ratio instead of using 1 plus K tau I to the n, because 1 plus K tau I to the n can be hard to deal with, especially tau I. I'm going to expand tau I, I'm going to get into concentration again. How can I separate these guys? It's going to become a whole shebang. So let's expand this. So I'm going to expand it into using your series, if you recall from your math. Can expand this using this series, 1 plus nk tau I, n minus 1, 2 factorial k tau I squared, and I basically expand this expression. However, you need to remember that tau I is equal to V total divided by n V naught, right? And this is for a number of CSTRs in series. And this is valid for n CSTRs in series, right? Just remember this. For n CSTRs in series, right? And they have to be equal volume. Where basically this expression, right? This expression right here, this is tau. So the tau in each reactor is equal to your overall space-time or residence time divided by n, okay? And this is the, sorry, this is the expression I'm going to use here. And I'm going to substitute this into this expression. And if I do this, Ca0 over Cai, substitute tau I with V over V naught n, you can see all the n's start canceling out here. And I end up with this expression, right? So I end up with this expression as n approaches infinity, of course, you end up with this type of expression. And as n approaches infinity, then this n cancels with this n. Here I have n multiplied by n minus 1 over n squared. They both cancel. And CA naught over CAF is equal to this expression. So I have an expression for CA naught over CAF in terms of a series. What am I going to do with it? This series, again, if you reverse it back to a normal form, this series is equal to exponential of k tau, okay? And this becomes your PFR for first order reaction isothermal, no change in volume on reaction for equal size CSTRs in series. So what we're doing here is we're deriving a performance equation for a bunch of equal size CSTRs in series. And what we did is we used the performance equation of one CSTR, we rearranged it to get the concentration of, or the ratio of concentration in divided by concentration out. We multiplied all these ratios to get an expression here, 1 plus k tau I to the n. I expanded this expression using series calculus to just get a larger series expression. I plugged in the definition of tau I, V total over n V naught, and then I just canceled the n's and I simplified it to get this series expression here. And then this series expression as n approaches infinity is equal to exponential of k tau. And this basically becomes your PFR performance equation for first order reaction isothermal, no change in volume on reaction. So this is the performance equation of E equals CSTRs in series. And just one thing we need to be aware of is that this was derived under the assumption that n approaches infinity, right? So even though we made the assumption, we should not forget it, right? Because we took the expression to a series format, removed the n's, and then removed the n's by assuming it goes to infinity, and then reversed it to another type of series format, right? So just be aware. And this is the performance equation for equal sized CSTRs in series. So therefore, an infinite number of small CSTRs gives the same performance as one large PFR of the same total volume. And proof is only for a first order reaction, but in fact, it's true for all reaction orders, right? So this is the same performance as one large PFR. So if you look at if you derive the equation for a single large PFR for a single order reaction, you're going to get this equation, exponential of minus KT. And we can do it if you want to. So if you're called for a PFR, the equation we said is tau over CA naught is equal to integral 0 XAF dxa over minus RA. For a first order reaction, this becomes integral 0 XAF dxa over KCA, right? This is equal to integral dxa over K CA naught into 1 minus XA. And if we basically rearrange this, CA naught here cancels with CA naught here, I'm gonna get basically what? So I'm gonna get tau K is equal to this integral. If I integrate, I'm gonna get minus ln 1 minus XA from 0 to XA F, and this is equal to minus ln of XAF. If I take exponential of both sides, I'm gonna get, sorry, minus ln XAF yeah, so if you take exponential of both sides, you're going to get XAF is equal to exponential minus K tau. Sorry, this ln minus ln of 1 minus XAF, right? Just rewrite this properly here. So if I cancel, if I just take this k to the other side and then integrate, I'm gonna get minus ln 1 minus xaf from 0 to xaf, and this is equal to minus ln 1 minus xaf. If I exponential both sides, I'm gonna get exponential of tau k, or minus tau k, right? I'll just move that minus and take the exponential, is equal to 1 minus xaf. And if you recall, by definition, we said that xaf is equal to 1 minus ca over ca naught. So basically 1 minus xaf is equal to ca over ca naught. Therefore, ca over ca naught is equal to exponential minus tau k. Okay, so you're gonna get the same equation. So basically what this basically numerically proves that the performance equation for an infinite number of CSTRs is equal to the performance equation for one PFR for a first order reaction, isothermal and no change in volume. And again, this is only valid for a first order reaction, but it's also valid for all order reactions. And you might get this on a test actually. Just show this and just be ready. Just understand the process, okay? And this is what this presents graphically. So basically, as n becomes higher, the performance of these two reactors becomes very similar. Okay, let's move on now. So in the case if I have multiple reactor systems, and now we're looking at the second case. First of all, we looked at multiple equal size CSTRs in series. Let's have a look at plug flow reactors in series. Okay, so if I have several PFRs in series, can give the same performance as one single large PFR, right? And this is something you need to know. This is the performance equation for a PFR. And again, let's have a look at, let's just recall what these represent. Ca naught is the inlet to the first reactor in series. Xa is 0. Xai is the outlet from the reactor. Minus R is the reaction rate within the reactor. And Xai minus 1 is the inlet to the reactor, right? So if I have a bunch of PFRs in series, the overall PFR performance equation is equal to Ca naught 0 to Xaf dxa minus Ra. And this is the same as one single large PFR, right? So the performance equation for having a bunch of CSTRs in series is the same as the performance equation for one single PFR, okay? And you can derive this. This is actually very easy. Very similar logic to the previous one. And then, if you recall integrals, you have the limits are the same. You can just combine them to just build one large integral, and you're going to build the large integral from 0 to xaf. So again, just remember, equal size CSTRs in series, as n approaches infinity, the performance equation becomes the same as the PFR. A bunch of PFRs in series of any volume, it doesn't matter, will give the same performance as one single large PFR with the same volume, okay? So again, this is of any volume. So if I have a small CSTR and then a large CSTR, this performance, so this V1, V2 is the same as having one large CSTR with V1 plus V2, okay? This is what this slide is saying. Okay, moving on. And this is the graphical representation. So if I plot 1 over minus RA versus X, PFRs 1 to 7 perform exactly the same way as one large PFR with the same total volume, right? Because the performance of the PFRs is equal to the area under the curve. And if I use 3 PFRs, 1, 2, and 3, their performance is exactly the same as one single PFR with the equivalent volume. Okay, again, if I divide into 7 PFRs, the area under the curve will be the same, so the performance will be the same. Okay, moving on. What about if I have PFRs in parallel? How do I arrange them, right? Let's say in this case I have 3 PFRs, 2 of them are in parallel. This one has a volume of 50 liters, this one has a volume of 30 liters. and this branch D, and then branch E, I have one PFR with a volume of 40 liters. You need to take note of this metric here. For optimum performance, arrange for the space-time in each path of the parallel array to be the same. So I want to arrange such that tau in this branch is equal to tau in this branch, right? And this will give me optimum performance. So how do you achieve this? If you recall by definition, right, tau is equal to V over V naught, right? If you recall here, tau is equal to V over V naught, and V is the overall volume of reactor. So I need to find a division of tau such that, sorry, I need to find the division of the flow rate, whatever it is. If it's volumetric flow rate, if you have a molar flow rate, you know, if you have a molar flow rate, it doesn't matter. You need to divide this flow rate somehow such that tau is the same in both branches. In this case, you're given the answer. So in this case, I tell you, you know, if my overall volumetric flow rate is V naught and I divide it into 1/3 here and 2/3 at the top, when I calculate tau, so again, tau is equal to V over V naught. So for the top limb, overall V is 50 plus 30 divided by V naught, which is 0.66 of V naught. So it's a third, sorry, on the top it's 2/3, so it's 0.66 V naught. And the overall space-time is 120 divided by V naught. In the bottom limb, if I divide the volume, in this case 40, by my volumetric flow rate, which is 0.33 V naught, is equal to 120 V naught, right? So therefore, equivalent to 2 PFRs in parallel with the same space-time, i.e. equivalent to one large PFR with a volume of 120 liters. So to optimize performance, I need to put them in parallel in a way, I need to divide my flow rate in a way to maintain the same space-time in both branches. If you want to divide this into, if you want to, you know, break this into an algebraic problem, so if I say tau total is equal to tau 1 plus tau 2, tau total is equal to basically V total over V total here, and this is tau 1, and this will be equal to V1 over X V naught plus V2 over 1 minus X V naught, and you just solve for X, right? You have all the numbers here, solve for X, you're gonna get the split. And the idea here is that because the space-time here and here are the same, this is equivalent to 2 PFRs in parallel with the same space-time, and 2 PFRs in parallel with the same space-time is equal to one large PFR operating by itself. Okay, so let's just recap PFRs here. In the case of series, okay, so for PFRs, if I have PFRs in series, as we said, in series, I have PFR of V1, PFR of V2 is the same performance as one large PFR of V1 plus V2, right? Okay, now if I, in parallel, if I have V1, V2, let's say V3, V4, doesn't matter. If I maintain tau to be the same, so I need to tau in branch 1, tau in branch 2, then this is just equivalent to one large reactor with tau B1 or tau B2, right? So this performance, once I balance out the space-times, becomes equivalent to the performance of one large PFR with a space-time of tau B1 or a space-time of tau b2, whichever it is, depending on how we calculate it. Okay? So these are the two cases in series and in parallel. Parallel, we need to look at space-time. Okay, moving on. Still looking at multiple reactor systems, and now we're looking at the case if when I have unequal size CSTRs in series. So let's look at this case. I have a bunch of CSTRs, again in series. However, unlike the previous problem where they were both the same volume, now they're all different sizes. You see this guy is intermediate size. This is a deep, large CSTR. This is sort of a wide, small CSTR, whatever it is. What's the deal with the situation, right? So again, let's have a look at the performance equation for a CSTR. V over FA naught, is equal to CA naught minus CA over minus R. Always keep this in mind when dealing with whatever reactor you're dealing with. And in order to determine the performance of multiple CSTRs in series, you can derive it mathematically, of course. However, usually there are charts in order to do this. There's software there's like models which can do this for you. However, Levenspiel is an old book, and if you go work with people who work in reactors in industry, a lot of times find older engineers, whatever it is, they like to use these types of charts for their systems. And there are graphical procedures. So if you go to Levenspiel and look at the figure 6.8, you'll see a graphical procedure, and this is very similar to, I don't know if you've covered the McCabe-Thiele and mass transfer, but very similar idea where, let's draw some slopes. Let's try to match the slopes to a mass balance. And let's try to read the intermediate performance over there. Okay, you can do it this way, of course, in case of unequal CSTRs in series. And you can really determine the intermediate compositions, right? If you want to, you can determine the intermediate composition this way. Alternatively, you can look at the chart. I'm not going to use this. I don't like using these charts. If you want to determine the intermediate compositions, I suggest just divide it into a bunch of smaller problems. So you divide this into a small problem, you get CA1, V1, and then you use this as an input to a second small problem here. Solve it, use the input as a third problem here. Solve it. If you want, if you're very comfortable with math, you can write all the equations down, combine it into one big equation. You can put it all in Excel, and you have a small model going. Instead of using these charts, I think this is the more accurate way. But for this course, for the purpose of this course, we're going to look at another type of thing where we're going to think about what's the best system for a given conversion, right? So I want to achieve a conversion of x2. In this case, I have two situations. I have first situation on the left-hand side, x equals 0, C naught F0. I have a first small reactor, conversion at the end of it is x1, and then I have a second larger reactor, conversion at the end of it is x2. Okay. Alternatively, I can switch them over, right? I can put the larger reactor at the front and then put the smaller reactor at the back, and I get x1, x2. Do you think both will perform the same? Intuitively, you might say, yeah, possibly, maybe, okay. However, this mixing profile in this scenario is extremely different than the mixing profile in this scenario, and they will not perform the same at all. So how do I define which one is better? Let's have a look at this chart, which is minus 1 over R versus XA for a CSTR. And what does this represent? So if you look, it's basically, this ratio here, 1 over minus RA versus XA, right? So it has all the terms for a performance equation. And if I multiply XA by 1 over minus RA, I'm gonna get V over FA naught, which is your area, okay? So just to recall, what would this represent? So if you recall, we said the performance equation for a CSTR is V over FA naught is equal to tau over CA naught is equal to XA into 1 over minus RA, right? So if I plot 1 minus 1 over R versus X, and if I divide this into a bunch of small squares and I calculate the area under all the squares, I'm gonna get V over FA naught, which is an indication of the reactor volume, or it can be the reactor volume if you just have any of these parameters, right? So the area under this chart is equal to this. So I'm going to use this graph to determine which system will give me a better conversion. And if I look at the first scenario where I have X1, so a small reactor will reach X1, X1 will be on the smaller side, and then the big reactor will achieve X2, small reactor volume here, large reactor volume here. Alternatively, on the other side, the big reactor goes X1, goes a long way, and the small reactor just finishes off the job. Okay, which one is better? As you can see here, there's a box which is highlighted, K, L, N, M. And this is an extremely important point. In order to maximize the performance of or in order to identify the best system, you need to find the system and you need to find the point basically at which this rectangle is the largest, okay? And this is really the approach. The best system for a given conversion, or the best combination of CSTRs of different volumes to achieve a certain objective, is obtained by maximizing this area right here. Okay, so let's have a look. So total reactor volume. So total reactor volume is minimum when the rectangle KLMN is maximized, right? So the overall reactor volume is minimum when this rectangle here is maximized. Okay, so which was it bigger here? Is it bigger here? Or depending on the chart, you need to read it carefully. However, if I just give you a chart, I give you a chart, tell you find the best combination of reactors of unequal volume. This is what you do. Okay, you need to maximize the area of the blue rectangle, which is KLMN. That's what we said. In order to do this, you need to change the two red lines until you need to change X until the two red lines are parallel. Okay, so again, I just give you this chart and you need to find the maximum area. So let's say you start with X1, you draw your KLMN line, you draw your two lines here. One is a tangent to the curve, one is between the two opposing corners of this rectangle. Check, are these lines parallel? If not, then this XA is not the right XA. Increase the XA, keep moving, keep checking this line until you find the two, until you reach a point where the two are parallel. And at this condition, the sum of the areas of the two gray rectangles is a minimum, right? So when these two lines are parallel, the area under this curve is minimum. Okay, and you need to understand this. So in case you have a CSTR, a combination of CSTRs in series of different volumes, and you need to determine what is the best configuration, I need to look at this chart of -1 over R versus X. I need to maximize the area of this blue rectangle, KLMN. And in order to do this, I'm going to change X1 until the two lines are parallel. So I'm comparing the diagonal of this rectangle versus the tangent to this curve. And the point of minimum volume and best performance is when the diagonal is parallel to the tangent. Okay? And this is the point where I have the highest conversion at the lowest reactor volume. Okay, so it's just a procedure, just be aware of it, and you might get on a multiple choice question or something, just be aware of this process. Okay, so now let's move on to the last, or second to last thought here, which is the recycle reactor. And this is a very common case, you know, recycle, you have a reactor plug flow, and I want to recycle some of the products to maximize my performance. So there's a new parameter I need to define, which is R. It's called the recycle ratio. It's equal to the volume of fluid returned to the reactor entrance divided by the volume leaving the system. Okay, so R is equal to the volume I'm recycling, which is this stream, divided by the volume leaving the system, which is this stream. Right, this ratio right here is the recycle ratio I'm using in this case. When you go to work, or when you go to industry to work, so be careful that, you know, sometimes some people define the recycle ratio as this guy over this guy, or this guy over this guy. Just be careful. In our case, we're defining the recycle ratio as this leg divided by this leg. Okay, let's have a look here. The performance equation for a recycle reactor is this, okay? Just know it. If you can read the derivation in Levenspiel, of course, but for the purposes of this course, you just need to know that this is the performance equation for a recycle reactor. And when looking at the chart of performance chart of -1/R versus XA, you need to take note of two things. The two things is that as R approaches 0, my recycle reactor performance approaches that of a PFR, right? So as my recycle goes to 0, if I have no recycle, my performance is just like a PFR straight through, nothing. This is sort of intuitive. However, as my recycle ratio approaches infinity, so basically as my recycle ratio gets very high, I'm recycling a lot of products, the performance of your reactor approaches a CSTR, okay? So you need to be aware of this. As R equals 0, performance approaches a PFR. As R equals infinity, performance approaches a CSTR. So for extremes of negligible and infinite recycle, the system approaches plug flow or mixed flow. Okay. And there's this chart as well in Levenspiel, very similar idea, which is the ratio of volumes, volume of a recycle reactor divided by a volume of a PFR on the y-axis here. And at the bottom, I have C over C naught, which is 1 minus X, minus conversion. And comparison of performance of recycle and plug flow for first order reactions. And what you need to know here is, so for example, if I'm looking at a recycle ratio of 2, and for K tau equals 5, then 1 minus XAF is equal to 0.07 and XAF is 0.93. Okay, it's just how you read this chart. And again, K tau is your dimensionless parameter. It refers to your volume, or you can use it to refer to your volume, etc. And let's have a look here just at this chart. As R equals 0, my performance approaches that of a PFR. As R approaches infinity, my performance becomes very similar to that of a CSTR. Okay, for a second order reaction, very similar idea. You can get the ratio of the volumes of reactors by looking at this chart as well. It's also available in Levenspiel, and similarly, as R equals 0, my performance is closer to a plug flow. As R equals infinity, my performance is equal to mixed flow. So you need to just be able to read these types of charts. You need to be, if I give you a true-false question, as the recycle ratio increases and the dimensionless group increases, what happens to this ratio of volume? Increase or decrease, stays the same. Just be able to read this chart and get some conclusions and infer some conclusions from it. And similarly, this table is in Levenspiel, is a slightly confusing table, but let me explain it right here. So what this table represents basically is here you see number of tanks, and this is basically a comparison of the number of CSTRs required to reach the performance of 1 PFR with recycle. Okay, just you can try to read it, but the idea is that what it's illustrating is basically the same as the figure, where if I'm using 1 CSTR with infinite recycle, it's the same performance as a PFR. If I have infinite CSTRs with 0 recycle, is the same performance as a PFR. If I have 10 CSTRs, they're equivalent to the performance of 1 PFR with a conversion of with a recycle of 0.11, or 10 CSTRs in series is equivalent to the performance of 1 PFR with a recycle ratio of 0.22 to achieve these conversions, of course, etc. Okay, this is just to show you sort of in a table what's shown on the previous figure. Okay, let's move on, and this is just examples. You can read them at your own time, but we've already discussed these conclusions. Okay, let's move on. Okay, so now let's introduce the autocatalytic reactor, autocatalytic case. This is the final case. So if you recall from the previous slide or from previous lectures, autocatalytic reaction is this: A plus R goes to R plus R. Basically, the product catalyzes the reaction to make it go much further. And if I plot minus RA over CA, I tend to get these types of curves, you know, they're not, they look a bit complicated, where if I have some recycle in the feed, some, not recycle, some product in the feed, my curve between minus RA and CA looks like this. If I have no R in the feed, i.e. pure A only being introduced initially, then the curve between minus RA and CA looks like this, and it moves backwards. Alternatively, if I plot 1 over minus RA versus XA, I get a point of maximum rate. And this is for autocatalytic reactions. So what do we want to do? We want to find, basically looking at 3 cases for an autocatalytic reaction. For autocatalytic reactions, mixed flow is more efficient at low conversions, and plug flow is more efficient at high conversions, okay? So the point we're trying to illustrate here is that if you have an autocatalytic reaction and you want to select the best reactor or the best combination of reactors, you need to understand that for low conversions, PFR, CSTR is more efficient. For high conversions, PFR is more efficient. And if I look basically here, this is the area under the curve. The solid block refers to the CSTR volume. The dashed block refers to the PFR volume. And at low convergence, if XAF is low, then you can see that the volume of the CSTR is much smaller than the volume of PFR. CSTR is better. If the volume is very high, if the conversion is very high, XAF is very high, you can see that the volume of PFR is much higher than the volume of the volume of a CSTR is much higher than the volume of a PFR. So PFR is the favored reactor. However, there does exist an ideal point where both of them perform equally well, right? So there is a conversion out there, or there is a conversion at which both CSTR and PFR will be equally good for your autocatalytic reaction. Okay, so let's pose this problem right here, or pose this question. For an autocatalytic reaction, what's the optimum recycle ratio, i.e. the recycle ratio which minimizes the reactor volume required? Okay, so let's say I have an autocatalytic reaction. What's the best recycle ratio to minimize the reactor volume? So recall the performance equation for PFR with recycle right here. V over FA naught is equal to R plus 1. If I rearrange it, basically I get tau over CA naught is equal to this. And if you integrate, you're going to get another expression. This is not the point here. So how do we find the optimum recycle ratio that minimizes the reactor volume for an autocatalytic reaction? Let's have a look here at this chart, which is minus 1 over RA versus XX. So this is 1 over the reaction rate divided by the conversion. And the black line is your autocatalytic reaction. So I'm going to compare 2 points. The first one is this rectangle right here, which is KL. KL multiplied by X1 minus XAF, which is, it is the red shaded area rectangle, you know, and there exists a point where basically area A1 and area A2 are the same, okay? So you need to, if I keep on changing XAF and looking at, and drawing this rectangle and comparing area A1 and A2, there will exist a point at which area A1 and A2 are the same, and this is the point of optimum recycle. This is basically my optimum performance point for an autocatalytic reaction with recycle. So the point I'm trying to make here, so if I look at 3 cases where I have the plot of 1 over minus RA versus XAF, for the case where the recycle is too high, so if I set my XAF, or you know, set the XAI to XAF to be too high, you can see that the average rate, or the average conversion rate minus 1 over RA is very high, and basically the areas of the rectangles are not the same, right? They're just, this area is just too high. If I get the recycle ratio right, then this area at this point and this area at this point should be the same. If the recycle ratio is too low, then you know the areas are not the same. The area under the curve is much larger than the area here. So the point to make is that at the optimum recycle ratio of the feed to the PFR itself is at a fractional conversion such that 1 over minus RA at the PFR inlet is the average value of 1 over minus RA throughout the PFR, right? So basically at the optimum recycle ratio, 1 over minus RA at the inlet. So basically, if I get XA0, or XA inlet in this case, and I look at 1 minus RA, is the same throughout the PFR, right? Is the same is the same as the average throughout the PFR. So if I take the average of these two, 1 minus RA will be right here. And this is just something to know when designing these systems. You won't really be tested on it. Just know it in case you deal with it at some point in your career. But basically, if you have an autocatalytic reactor and you want to identify the best point of recycle, you need to look at this chart and basically just move your points, or move your inlet and outlet conversions in a way such that the area of A1 is equal to the area of A2. Okay, so this is the end of this lecture. Let me just recap the important points we covered today. So, as you prepare for your test and other things. So I'm going to go to the very beginning and quickly just go over some of the important points we have. So again, just exam 1 will be September 29th during the regular lecture time. It will cover weeks 1 to 4. Next week, we're going to have some review. And we compared the size of single reactors for a first order reaction, compared the CSTR to a PFR. You have this chart which shows you this, n equals na. And if you compare the volumes, in order to achieve a much higher conversion, the ratio of volumes increases exponentially. So if I want to increase my conversion of 0.9 to 0.99, I need to get the CSTR 100 times the volume of a PFR versus only 10 times. But at all points, the volume of a CSTR is much higher than a PFR. We looked at the case then for using a larger CSTR versus numbering up the CSTRs, so using n number of CSTRs of equal volume. And we found that using n number of CSTRs of equal volume performs much better. And these are the conclusions which you need to be aware of. So we've talked about second order reactions as well. Then we talked about equal size CSTRs in series, how n equal size CSTRs in series perform the same as one PFR. And we looked at this chart, we looked at different cases, we derived the equation and how it's the same as the performance equation for a single PFR. We then looked at multiple PFRs in series, multiple PFRs in parallel, and we set the metrics. So if you have multiple PFRs in parallel, the overall, so if you have multiple PFRs in series, they will perform the same as one large PFR with the same overall volume. If you have multiple CSRs in parallel, they will perform as a single PFR equivalent to the space-time in both legs, as long as the space-time is the same in both legs. So the optimum performance, I need to arrange them such that the space-time is the same in both legs. We then talked about unequal size CSTRs in series. We talked about this chart and how to read it to get the best, the best arrangement of CSTRs in series. We talked about this procedure where I basically connect the two diagonals here, connect the tangent here, and find the point where the two lines are parallel. Then talked about this recycle reactor and how, as the recycle approaches 0, it's more of a PFR. As the recycle approaches infinity, the behavior is similar to CSTR. And then finally, we talked briefly about the autocatalytic reaction. And just what you need to know here for the autocatalytic reaction is that there is a point of optimal recycle, and the way you read it off this chart is that it's the point at which the area under the area in this semicircle here is equal to the area in this sort of triangle here. So basically, the optimum recycle is when your curve looks like A1, or the curve is at the point where A1 and A2 are equal. Okay, so this is this week. Homework number 4 will be posted, and the solutions will be posted as well. Please go over them, study your homeworks carefully, get prepared for these types of to address these types of concepts. Sorry, it's homework number 3. Get prepared to address these types of concepts, and please come to office hours if you're not clear about anything. Next week will just be a review week in preparation for your exam, and we'll basically try to go over the important or the points that you'll be tested on in that exam. Thank you very much.